This is a tutorial about how to use the course model builder in UTAPWeLS for creating uh, 2D or quasi 3D models that can be used with the UDAR simulators. So the model that we want to build in this case is called Benchmark 2. It's one we use for testing the software a lot. Um, it has two faults with dip and azimuth and trajectory intersections. And we have vertical and horizontal resistivities defined at each one. And and then this is what it should look like when we're done. And we'll be able to see both the horizontal and vertical resistivities in each block. And keep in mind that it specifies a specific true vertical depth for the start. So I'm just going to copy that. And then we can create a new well. And first thing we want to do is add a trajectory. We could put explicit values, but I'm going to show you how to import a survey file. So since we don't have any yet, I'll hit the plus so we can add one. And I'll select this one. And now you see that there were many options for the formats of the survey files you could use. You can have as many columns as you want. And you're just going to select the ones. So in principle, you could have multiple surveys defined in this same file. But you only need three for each survey in UTAPWeLS. You can either have X, Y, Z in these two formats or MD inclination azimuth. So in this case, the first three columns here are MD inclination azimuth, so we're going to use those. And it already picked up the first three columns here, so these are set, but you do have the choice if you wanted to use different values, you could. And then you need to pick the unit for each column up here that you choose. And so for the depth, we'll pick feet and degrees for the others. And then the final thing, notice over here that when we selected this, it set the true vertical depth to be the first measured depth, but that's not what we want. We want the one that was designated uh, in the model. And so we're going to change that to this value, which just moves it a little bit up. Okay, so we now have our trajectory at the position that we want it. And so now we can open the course model editor from the UDAR menu. And notice in here that first you have the boundary control, so you can select what region you want to create your model in. Um, and you want it to include the trajectory and whatever relevant resistivity regions you want. So we saw in the model that we had some resistivity below the bottom of this one, so we want to extend this down to 17,300. And notice that the Y, because we're going to have angled faults, it's important. It may be important to have uh, a significant amount of Y range in this, which is the position into or out of the curtain plot plane. And then we have tables for the faults and boundaries. And so what I'm going to do first is, since we saw that each block, which is what the faults divide this into, had three or four layers, I'm going to just start by adding four layers in here at approximately the right position, or four boundaries, I should say. And then when we add the faults will automatically divide these up into separate blocks. And they don't have to be exact right now, so then we know that one fault, we can add a fault here. Was at around 2,800, and the other one, we saw that it crossed a little bit past 2,000, so I'm going to give it some angle and have it pass the trajectory at a little bit past 2,000. And then, so now we can see if we set this to be 90. That it's not quite at the right position according to the model. We want this to be at 28,000 or 2817. So in fact, I'll just copy that. And so I'm going to put the second fault at exactly that position and then reset this to 90. Okay, so now this is in the right position. The first one, we can see if one way we could move this around and use the position indicator here to try to get the right position. And another way that we can check this is to look at the path intersections here. And we see that we are still a little bit off, so I'm going to adjust the starting point to be 1893.4, and then when we set this back to 45, we see that we're within an inch or so of the correct position. Okay, so now we have this, and now we want to adjust the layer boundaries. So we'll notice that now we have 3 blocks that were created by the faults. And so we can adjust each one independently. So I'm going to set these at the starting points at the positions indicated in the model. And then we can set each of these dips to 0, and that will put these all exactly as they were indicated in the model. Okay, so these are the correct positions for the first block, and so now we can go to the second block. And the second block we have the first one at 1750. So we could move this down to around 1750 like this, or we can set it exactly at 1750, which is what I'll do in this case. And since these are all moving down, I'm going to start with the bottom one, which should be at 17,150. And then the next one should be at 17,120. And the next one should be at 17,110. Okay, and then I can, again, adjust all the dips in the same way. 0, 0, 0, 0. Okay, so that's the second block is designated by the model. And then the third block, again, we could adjust these manually if we wanted to. But and recall that in the third block, we actually only had 3 layers. And so we'll probably have to get rid of one. So let's just set these. I'll set the first one at the correct position, which is 17,130. Oh, I got to change it to block 3. Okay. 17,130. And then the next one is at So actually, I'm going to get rid of the middle one here. So you can, if you click on a layer or a fault, you can hit remove that layer or remove that fault. So this is just going to remove this one. And then I'll set the second one at the appropriate position, which is 17,180. And this one is 17,230. And then once again, since all these faults are horizontal, or not all these faults, but all these layers are horizontal, I'll just set these to 0. All right. And now, last thing we need to do here is that according to the model, the 45-degree fault has an azimuth of 45 degrees. So I'm going to set this azimuth, and in the model, it designates the azimuth from the curtain plane. So that's the way that this is designed from the curtain plane. But as I'll show you, you can also see what it will be in terms of the global dip and azimuth. And then this one is at 70 degrees. And then if you want to see the global dip and azimuth for these faults, you can click on this. And you can see that the one that goes at 45 and 45 from the curtain plot, in actuality, the dip angle from the curtain is going to be, the dip angle in the normal terms is going to be 60 degrees and 54 degrees azimuth. And then the curtain azimuth will be 144 degrees. And this one will be 160 degrees. Okay, so now we can start filling in the resistivity values. We have everything where we want it. And so I'm going to start off in here. The top layer is, so we'll do the RH first. And notice that if you want, you can do these, like if you're just changing one, it might be easier to set the resistivity by the block. So I could set this one to 2 and this one to 5, which is what's indicated in the model. But it's kind of easier to do it here, where you can just click all the positions in the whole model. So this one is going to be 2, 2, 2, then 1.5, 1.5, 1.5. And then this is 30, 30, 30, 30. And then we have 20, 50. And then this one is also set to 2. Okay, so that looks roughly like our model. And then we'll do the same thing for RV. In this case, we have 5s up here. 5 down here. And these are all going to be 4. And then these are going to be 30 again. And this is the same, 20 and 50. Okay, so now we can go back and forth between RH and RV. Um, and if you recall the model, this is indeed what it looks like. Okay, so now we can notice down here we have several options, and the one we're going to do first is we're going to write this model to a HDF5, give it a name, and here it tells you how many grid points you'll have, and that gives you an idea of how big the model is going to be. Usually, we have it somewhere between 1 million and 50 million. But usually around, something like 10 to 20 million. So, but here we need some more Y values. So I'm going to set Y to be 5 and set X to be 5. And so these are the grid sizes, and we'll set this to be 1. And so that gives us close to 50 million points, which is okay. And then the logging points, this will determine how many logging points will be within this region, evenly divided. And if you feel like you need more detail in your, and this will determine, for instance, what values will be written by the simulation. So if you feel like you need more detail, you can have more. Maybe I will put 200 here. And then we can, a lot of times in the name, I'll put like some detail that says what this particular grid definition is. So like 5, 5, 1, and then maybe 200 or something. Okay, so then you just hit write, and you, I see. I guess it doesn't like that for the names. I should use dashes. So we'll put 2 dash 5 dash 5 dash 1 dash 200. And then the writing is pretty quick. Okay, so now that's done, and now we can simulate or we can view it. As I said, this creates a quasi 3D model. So first I'm going to just show you that I don't want to get into exactly how you do it because that's not what this video is about. But we can view this model if you open it up. This is one that I made for the previous well, but it's the same model. You can open it up in the 3D viewer by just selecting it, loading it as a pixel-based model, and then adjusting the model viewer until you see it. And then you can adjust different planes in here to get different views. And you can see here that from this view, it looks just like the model picture. And but from this view, we can see that we actually have a the azimuth for these layers. Okay, and then if we want to simulate, you have the choice of 1D or 2D. So if we simulate 1D, then it's a fairly quick simulation. Um, and you can choose which the tool sensor configuration as far as frequency and spacing. We have a couple of defaults set, or you can make a new tool if you want. Um, you can add a tool and then you can add, some default settings, or you can add as many new settings as you want. And you can add the logging point spacing for the simulation. Um, in this case, because this is not done from the HF5, it's done directly from the model. You can make the logging point spacing for the 1D to be anything you want. And then down here, we have the output parameters, like what format you want the output to be. Do you want magnetic field logs or voltage logs or conductivity logs? And then the depth point reference for the tool, and different tools use different depth point references. And then you can set the name. If you do multiple of 1D or 2D, you might want to change the name indicating the differences. And then likewise, if you go to 2D, here we can set this default here, which has a lot of two different spacings with a bunch of different frequencies. Down here yeah, you have to select a HDF5 path, so we'll select the one that we just made. And then you don't have to simulate all the points. This is especially important if you do a 3D simulation, because it may take a long time. Maybe you're only interested in a certain region. So you can select what points you want to do, either by the index of the points, or by the index range, or by the MD range. In this case, then we'll just assume all. And then here, this one, you have to sort of play with. It depends how much detail how precise you want the simulation. If you just want a quick rough idea, you can do um, the low resolution, which will be the fastest. You can do a medium resolution, and if you really want to make sure that you get every detail, you can do the high resolution. This is for the internal simulation grid. And the low resolution sometimes will have some slight offsets, so it might be better to have a higher resolution, but it is a lot faster if you just want the rough idea of what's going on. And then you just hit simulate, and what happens is then it will run, and I'll show you what we did in the first well. So then you get these in both either 1D or 2D, and you'll get all these logs for all the different components of that measurement. And then we can look at that and we can look at those logs here. And as you can see, because we didn't do a 3D, the YZ, which is an indicator of 3D effects, is pretty much 0 for the 1D or 2D, but we can see effects based on the resistivity for the other magnetic field logs. And then we can also have the option up here to do inversions. And so if you open that up, you can select different inversion folders. Oops. think, oh, yeah, sorry, I didn't run that one. So we'll open the two. Um, we look at well one, and you can do invert, and it will bring up all these settings. You can do uh, ones with priors, so you can do first or second pass uh, inversions, and uh, and then the final result. If you hit results, it will display uh, something like this, and here you see here you see the inversion results, and you can look at RH or RV, the uncertainty plots. You can change the limits, and up here it gives you the misfit, and over here it gives you a confidence interval. And then you can move this around to change where you look at the confidence interval. And you also have the option, if you select either Model H or Model V, if this was done from a UTAPWeLS model, um, you can slide this to go from being the inversion results to being the model results. So you can overlay them and see how well it did. And here you can see that the inversion is pretty much right on top of the model that we used to generate it. So that is the inversion and the pixel-based model viewer. We'll look into more later, but this is how you use the coarse model builder.